Okay, good morning, everybody. My name is Greg Kurtz, and we'll be starting our presentation shortly for October's Dig Deeper. We're just waiting for a few more folks to join us this morning. Okay, looks like we got a pretty good group here this morning, so we'll get started. Let's get started. My name is Greg Kurtz. I'm the technical director for the International Ground Source Heat Pump Association, and we're happy to present our October Dig Deeper webinar and hope that you enjoy what we have for our topic speaker and presentation today. But first, I got some news items that we're going to want to go across just for our members to get updated of what's happening at IGSHPA. So first, we'll start saying that, here we have our town halls and Dig Deeper webinars. We are still accepting abstracts for the town hall for 2025. We got one left. And then we are accepting 2026 abstracts for the town halls and Dig Deepers in the 26 year. So if you're interested in doing that, you click more on our website at igshpa.org for training and events, and let us know what you're interested in doing. But today we have Al Wallace doing a presentation on optimizing geothermal heat exchangers for ground source heat pumps and radiant hydronic systems. And he'll be doing that with us today. Also, we have another news item to talk about, and that is our exciting 2026 annual conference. It's going to be this year in St. Charles, Missouri, which is just outside of St. Louis, Missouri's airport. So it'll be easy to get to. We're ready to take registrations. The hotel information is on our website, sponsor information. If you're interested in being a sponsor or an exhibitor or submitting an abstract for the presentations for this year's conference, please save the dates. April 13th through the 15th is going to be our conference, and we had a really good one this year, and we're expecting this spring's going to be awesome as well. So you might want to definitely put that on your calendar and give it some consideration to attend and visit or present or sponsor. And we can't thank our sponsors enough for helping us do this. And so we already have quite a few sponsorships taken, but there are a few blanks available yet, as you can see. So if your company is interested in becoming a sponsor of our conference, again, we're accepting sponsorships for that. There are lots of booth spaces in there. So if you want to exhibit, we have a lot of booths available. They're 10 by 20s, 20 by 20s. If you want something custom, you can also ask for that. And maybe Sally Stevens in our marketing department can help you do a custom booth. Maybe you want something larger. But at any rate, we have some open spaces yet for exhibiting, and some of them are already filled up. So we got a good start on that, and looking forward to this year's conference coming. Also, we have cooperation with the IEA group over in Vienna this year. They're doing their updated technical conference on heat pumps, and so IGSHPA is working with them on that. This is more of a research university type conference. It's not the exhibitor style conference like we are going to have in April of 2026 for our North American industry folks. But if you're interested in those kind of things, there's a lot of technical papers and things that will be discussed regarding heat pumps at that conference in Vienna this year. So we have a link on our website you can go to find out more details about that as well. We also have a lot of new things on training coming out, and some have already came out this year. So if you see our website training link, you can find Jeff has updated a whole lot of new information about our new courses that are released or coming out, as well as some of our current courses that are already available. So you certainly want to check that out if you're looking to learn more about the ground source heat pump industry and all the different courses we have for this. This would be a resource to go look at and learn more about them. With that, a lot of the new courses are also put out in conjunction with the newest edition of the C448 standard. So this is available now as a new standard. It came out in May of this year. There's been a lot of new updates done to it. They have a consolidation of a lot of redundant clauses that were in the earlier version, and now it's nearly 250 pages. So it's been updated quite a bit by the new standards group, I guess, that review this, and it's certainly something that I think you're going to want to look at and become familiar with. We have a significant price discount for IGSHPA members. They license these as a PDF version, and you can get a discount on it through IGSHPA. As also is the basis of a lot of our new training. We've tried to incorporate the standards with our new training course materials, so you're getting the latest of everything, industry standards as well as industry best practices. As you know, the old 2017 IGSHPA standards have been sunsetted and being replaced by the C448 new standard. So we are in full support of this, and it's the new way that things are moving forward for design and installation of ground source heat pumps. We are also looking for input from our members. If you happen to be a company that have a lot of geothermal experience, you've got jobs and projects. We're always getting inquiries at the association from people in the public who are looking to do a geothermal project and want to understand more about them. So we're taking information from any of our members that would like to submit some data from your projects that would make good case studies and so forth. Again, on our website, you can go to the About IGSHPA link on our web, and then you can find the project database. And I think there's some links there that let you give us some input on that. And we'd like to add your jobs to this to help people find the information they're looking for, whether it's a school or educational building or a commercial building or residential home. We get lots of inquiries from all over that are looking for different projects similar to theirs, and they'll go to these databases and search them. So the more we have on there, the better for everybody to find the comfort and information they're looking for about moving forward, maybe on their project. So let us know. We need your help if you can do some feedback for us on that. Also, we have our Geo Outlook magazine. It was published in July, and we are now accepting articles and ads for the January edition, which will be coming out. All of our magazines are made available online back to 2003. So we have a pretty large audience that looks forward to reading this magazine, over 6,500 plus people and growing. And if you're interested in doing articles or ads for that magazine, they stay as long as that magazine's online and out there. So you can send email to info@igshpa.org for further details. All of the town halls and dig deepers and the annual conference qualify for CEU credits. So it's important if you like CEUs for this webinar, please send a chat message while we're on this Teams meeting to IGSHPA. Please include your name and email, and the CEUs are listed there. You get one per contact hour, and the certificates are sent at a half-hour CEU intervals. So we do provide CEUs for watching today's webinar. Another option for obtaining CEUs is that these IGSHPA Dig Deepers and town halls are all recorded. So if you're watching this after today's presentation and watching it later on our YouTube channel through our webpage, there's a Dig Deeper webinar code, as you can see on the screen here. You may submit that to get credit for watching it even after the actual live event. So there's no changes for individuals attending live or recorded, but you want to submit that code to get the credits. So if you'll send an email to info@igshpa.org, you can request the credit. So last couple items for housekeeping. Once we start, we'd like to ask you to use the chat for your speaker questions. Just type your question or any other comment in the chat or the Q&A area of the webinar, and the web facilitator is going to try to field them for the speaker after he's done presenting. And if by chance we don't get to your message today, we'll do our best to get back to you as soon as possible. We will be recording this session for viewing later. So Feel free to look at this later if you want to review more about it. So here you're going to see on the submission of questions for the chat or the Q&A. Sometimes people have had some difficulty using the chat, so you might want to look at using the Q&A area. And if you clicked on that and you got a dialog pop up as you see here on the screen, you want to click the OK. Usually that allows you to go ahead and do it. And you can submit your questions after that. But if it doesn't work for you by chance, you can raise your hand through the webinar here on that icon to raise your hand, and we'll try to recognize you and take your questions. And finally, we have a few disclaimers of potential conflict of interest we have to announce. So the upcoming presentation represents the opinion of the presenter and does not represent any official position, opinion, or endorsement of any products or services by IGSHPA or its members. IGSHPA Town Halls and Dig Deeper webinars are member updates and education on the latest information in the geothermal heat pump industry and are not meant to endorse one technology brand over another. It is the presenter's responsibility to disclose any conflict of interest or position that may arise in the content of the webinar. So let's get started with our speaker. And today I'd like to introduce you to Al Wallace. And Al is the owner and principal of an Energy Environmental Corporation. And his presentation today is on optimized design of ground heat exchangers for ground source heat pumps and radiant hydronic systems. So Al is from the Denver, Colorado area, and I'll turn it over to Al, and you can queue up your presentation, and we'll start with you. Let me know if you're ready
Thanks,
to go.
Greg.
Yeah,
Do you see the presentation on the screen in the right format?
I do see it. Yep, you got full screen. Everything looks good.
All right, thank you. I appreciate the invitation to present today, and I also appreciate those on this call taking the time to look at these new and exciting ways to design ground heat exchangers. Just as a quick background, I've been doing this for 25 years, starting as an installer and a designer, actually starting in small residential systems and expanding to very, very large custom homes up to 30,000 square feet. And I still do design and consulting for commercial projects that are fairly substantial. A context of how I'm presenting this is I have a degree in engineering with an MBA. And after 2 careers, one in the Air Force and then in the dot-coms, I went back and got a master's of architecture and landscape architecture. And a lot of that was focused on integrating the building with the land, which is clearly what geothermal does. But in that context, I also learned that architects hate systems and I didn't like CAD. So I said, I'll do the math and you do the drawings. And we still carry that forward today. I'm the president of Energy Environmental, but also a new organization we just formed to expand geothermal infrastructure in the United States called Forge Geo. If you go to forgegeo.com, it gives you more information on that. And at the end of this presentation, if you stay online, I'll actually talk about some really exciting opportunities where Forge Geo has funding to provide design services. So if you're a residential contractor trying to move up to larger projects or a detailed design engineer for large geothermal systems, and you need some help either checking numbers or with design, there's services available for that. We're going to back up a little bit in history and look at innovation through simplifying systems and integrating systems. When you got in this presentation, you're probably thinking that I'm talking about thermally conductive grouts or how to do geothermal installation or whatever. But in fact, we're completely changing the way we look at the way we do business. And going back to historical precedent, the first thing I want to point out is you have to understand customer and industry bias. Henry Ford said, if I asked people what they wanted, they would have said a faster horse. And if we talk to installers or engineers, what do you want? I want a heat pump with a little bit of better COP, or I want to make the trenching easier or drilling easier, or whatever, which are incremental changes. And we're talking about radical design changes. The other thing is overcoming resistance to change. In a book called Disciplined Entrepreneurship, Bill Otlett shares a story of the inventors of Ethernet went to an industry conference and most of the experts there were from IBM promoting the token ring network, and they were poo-pooing Ethernet. So they gave all these technical reasons why Ethernet should never work. And he says, well, I guess it does not work in theory, only in practice. So in the back of your mind, if you're thinking that some of the things here do not really work in theory, I would ask you to have an open mind. The exact implementation of some of these concepts we've been doing for 10 years on small and very large projects, and it truly does work. And the last point is, we don't design heat pumps from scratch. We basically buy the heat pumps, put them together in a system, just like when you're building a car. You buy the engine and transmission, you put it together. You don't try to put the engine together by itself. In this case, we still do that with geothermal heat pump pumping stations and some of the distribution, where we could be buying those as commercial off-the-shelf products. And I'll be talking about that in this presentation. So rather than settling for incremental gains, I'm suggesting we pursue radical transformation, and that's redesigning the ground source heat pump systems with the ground heat exchanger, the pumping, the design of the actual layout of the piping, deploying dual process heat pumps. So in the case of an example, if this heat pump has a COP of 3.5, if you look at technology like reversing chillers, it heats one source while it cools another source. So you have a sports center that has a swimming pool and an ice rink. You basically are heating the swimming pool by cooling the ice rink without the ground loop. So if you have a dual process in your architecture somewhere, you actually double the COP from 3.5 to 7.0. And then we're going to talk about advancing hydronic distribution for breakthrough efficiency. Hydronics inherently use half the power of blowing air around just for distribution. And they also enable zoning fairly easily. And with the pumping energy being half that of blowing air, by integrating hydronics with geothermal systems, you basically have two water-to-water technologies that work very well together. Historically, we've basically been challenged with our own standards not fitting owner priorities. And we're going to show a slide with the evolution of technologies over time. From an IGSHPA 1987 foundation all the way to 2025. And we incrementally change the excellence of implementing ground heat exchangers, piping, flow rates, et cetera. But we haven't been focused on the owner priorities. And those priorities include operating efficiency and simplified controls for commercial buildings, and also integration for district energy systems, and sustainability. For homeowners, the number one priority is energy efficiency as it relates to operating costs. In a survey by DOE and some other agencies that I cite on slides, homeowners are basically most concerned about the operating costs of their heating and cooling systems. But if you look at high-end custom homes and some of these projects that are less financial focus, so instead of commodity-based pricing for the cheapest system, they're building their forever home and they're focused on comfort and long-term maintenance with low maintenance. And their priorities aren't dependent on tax credits, which expire this year, and it's causing great consternation for residential contractors. In 2018, we saw the heat pump business drop off by half. Part of that was due to the recession in 2009 and 2010, we had a recovery, but then it fell off. And the same thing's probably going to happen with the residential tax credit. And I'm proposing don't sell on the tax credit, sell on performance. If you look at air source heat pumps as a competing technology, there's a time and a place for those. It'd be very difficult to convince a homeowner to put in a ground source heat pump in a very mild climate. And I'm going to go into a lot of detail on that later on climate zones with air source heat pumps and show you where most air source heat pumps are targeted for and where they're installed, and also where you might have competitive advantage based on historical numbers of where ground source are installed. And lastly, lack of certified geo exchange designers and contractors, especially for large installations, is a real problem in our industry. And what we're trying to do is we're going to try to simplify that process so that if you're either a standard engineer designing heating and cooling systems and you want to get into geothermal, I'm basically giving you the approved solution with modular components that you can plug and play. You don't have to be designing the engine or transmission from scratch. You basically have a footprint for an architecture that's well proven. If you're a small residential contractor and you want to get a larger custom homes, these solutions I'm presenting to you are very easy to install. And it's based, as I said, on 25 years of our company starting off very small and moving into this business. So we're going to look at climate zones with air source heat pumps and how they work in the industry. We're going to provide some target building size. Clearly, we don't want to put a $20,000 pump station into a 3-ton residential house. And at the same time, if you have a 200,000 square foot building, unless you can break it up to smaller sizes for systems, it's not optimized. So we're going to have a target building size between 5 and 30,000 square feet, which equates to about 7.5 to 60-ton capacity. The proven modular architecture that I'm going to show you, Energy Environmental actually patented this back in 2012. There's certain aspects of it that you should probably look at if you're designing systems like that. But under the modular components that we provide through GeoFlow Corporation, it incorporates all that intellectual property into the cell of the equipment. There is a 12-step best practice framework. This presentation is normally a 3-hour webinar, expanded much more than the 20-some slides that I have here. But it's also a 3-day course by Forge Geo to give you a background on optimized ground heat exchanger design with heat pumps. On the next slide, I'm going to show you some references you can go to now and get articles on this subject that I had written for Plumbing Engineering Magazine. And lastly, I'll talk about Forge Geo as an organization. So if you go to PHCP Pros, there's a link right here, phcppros.com, and articles. Article 21913 is part 1 of this series, and Article 22199 is part 2 of the series. And there's about 8 or 9 pages of detailed information that go through each of those 7 or each of the 12 steps that I talked about. The other source you have is, I'll give you a source for our patents. There's a 17-page specification that provides very technical information on how and why these systems work. So if we look at designer priorities, going back to the first IGSHPA standards, it's been all about ground thermal properties, temperature drift, hydraulic design, having the right size pipes going down the hole, and then the pumping energy that was required to pump the energy through the pipes at maximum load conditions. And part of the requirements was to have hourly load calculations, which is highly recommended. In fact, it's mandatory for code standards these days. But it's also critical to feed that hourly data into modeling programs for ground heat exchanger design. These priorities 1 through 7 are the engineer priorities, but ironically, their priorities 8, 9, and 10 are more focused on what the owner priorities are. And that's really critical, because what we're focused on as engineering is not necessarily what we're necessarily delivering to our customers as far as value. So we need to take a look at that. If you want to address heat pump and interior piping, it's using factory built components, using onboard controllers, or using functions in the heat pump. There's an article coming out in Plumbing Engineer, what I had on the prior slide, and said if you want to simplify DDC controls, you tell the heat pump what you want, you don't tell it how to do it. So you say, I want stage 1 heating, stage 2 heating, stage 2 cooling, or whatever. You don't say, okay, turn on the load pump when I turn on the heat pump. Because if the load pump is only tied to one heat pump, you should use onboard controllers for the heat pumps. That eliminates control points and makes it much simpler. And then on the economic justification, we have to be able to provide justifications for the investment. And if you use simple payback, it never pays for itself. But if you use a life cycle cost analysis, which incorporates operating costs, it's a better module to use. So if we go back to the geotechnical standards I talked about, 1997, IGSHPA published their first standard. IGSHPA was founded at Oklahoma State University, so it's very technically focused on heat pumps and ground heat exchangers. 1997, Steve Kavanaugh and his partner Rafferty came out with a book which has been updated in 2024 on design standards for heat pumps. And then in 2025, CSA, ANSI, and IGSHPA came out with a C448 standard this year in May. And it's got an improvement on the previous standard. So ground heat exchanger design, system design, et cetera. And the CSA standard, they added things like thermal conductivity testing for energy piles. And they also added integration for systems like standing column, wastewater, surface water, and other process heat exchangers, which improve ground heat exchanger efficiency, but they don't provide details on exactly how to build those. They do mandate that the heat exchanger circuits and the distribution circuits in the building be hydraulically balanced. But again, they don't tell you how to do that. And to be completely honest, if you have the exact same flow rate in the ground heat exchanger as the building, as you're going to see in some of the piping diagrams, it's very difficult to balance both at the same time at optimal performance, especially for partial loads. This next slide is showing climate zones in the United States. Excuse me, it's showing penetration in the United States of heat pumps, which are more focused in the Northeast. These are climate zones 4, 5, and 6, and 7, which I'm going to show you on another slide. But on the, I went a slide ahead too far. This is a pretty busy slide. What I will apologize right up front is normally with presentations, especially for business world, you just have the major bullets for your presentation. But the intent of this slideshow wasn't just for presenting the data. It was allowing you to go back and look at it later, print out the PDF copy. And if you want a copy of this at the end, there's an email where you can ask for it from ISCA, or you can send me an email, and I'm happy to send you the PDF of this presentation. But this slide shows the penetration in the United States by climate zone. So Hawaii is down here with Florida in climate zone 1. As it gets colder going to the northwest up to Alaska, it goes up to climate zone 7, which is in the purple here. And then if you go from east to west, you have moist zone on the east, dry in central US, and then the marine climates in the western US. This is a population map of the United States. And if ground source heat pumps were universally adopted by all population centers, and you would see with heating or cooling equipment or air conditioners, this map penetration should map directly with the population centers. But what we actually see is in the Northeast, we tend to see a lot of ground source heat pumps. Even though we have the same climate zones in the West, we don't have that penetration. So Northeastern US and then Washington, Oregon, and Idaho have high heat pump installations, as we're going to see on the next slide. Air source heat pumps are predominantly in this region. And if you look at the ASHRAE numbers, with a low of 35 degrees, say in California, an air source heat pump works very well. It'd be extremely difficult to convince an air source heat pump potential customer to spend money on a ground heat exchanger when the efficiency is fairly close to geothermal and thousands of dollars less. Yet we still find these colder climate zones with temperatures getting down to 25 degrees where we have a big installation of heat pumps. So zones 1, 2, 3, and 4, which are these numbers right here, these colors here correspond to 1, 2, 3, and 4 climate zones. They're predominantly air source heat pumps. And there's 2 anomalies in there. If you look at Florida and Texas, this is shipping data from the Department of Energy for water source heat pumps. And they said basically 19% of all the heat pumps are water source. So they're not ground source. They use a cold building loop in a commercial building for their source. So the numbers could be skewed as far as ranking of penetrations of being 5.5% or 4.3% in the US. It could be skewed because they're water source. And it's not 20% per state, it's 20% for the United States. So this, all 20% could be down in Florida, and I would just caution against that. But when there's a number here or a state in green, that means they're primed for air source heat pumps because they're in this climate category. If they're in red, it's extremely difficult to sell ground source. So even though, for example, Georgia might have penetration of ground source heat pumps, if you look at Alabama, Mississippi, Louisiana, probably because of economics, you're not going to see any ground source heat pumps, and it's going to be tough to sell there. Same thing with Hawaii. On the other side, if we look at the top installations of ground source heat pumps, these highlighted areas in yellow represent 50% of all the heat pumps in the United States, ground source heat pumps that are installed. And the majority of those are in climate zone 5A. So it's moist, and it's the northeastern states that you see here. And that's really no surprise to anybody in the industry. And lastly, if you get into zone 6A, which is fairly cold climates, you see a lot of heat pumps installed, with Minnesota and Michigan also being in the top 11 states that constitutes 50% of the heat pumps that are installed. The last thing I'll mention is this chart has the load imbalance. So if it's negative, that means it's primarily cooling mode, and that's 4,400 degree days that are imbalanced, more cooling. When we go to Alaska, it's 10,000 degree days in heating, which is the imbalance. So if you take the degree days in heating and you subtract the degree days in cooling, that gives you the imbalance. The way that affects ground heat exchanger design is the greater the imbalance, the higher the cost of the heat exchanger, unless you're able to offset those loads. For example, in Vail, Colorado, we have an unbalanced load, which is heating dominated. But for a library project in Vail, we were able to use exhaust heat from the ice rink next door that was also owned by the city or the town of Vail, offload heat from that ice rink, the rejected heat from the ice rink, and that actually balanced the loads that make the ground heat exchanger smaller. So this map in green is the shipping data from the Department of Energy, and it includes ground source heat pumps. And the number one state is Ohio, then Pennsylvania. And the ranking by state with the percentage installs is on the upper left corner. You have Illinois at 5.6, Florida and Texas. I think these are mainly water sourced, because in my experience, I don't see the number of ground source heat pumps installed there. Texas could be Austin or the Hill Country, where there's some more money. That could accommodate for that, but I think it's primarily water source. Then you got New York, Indiana, Minnesota, Missouri, Michigan, and Iowa. These constitute the top 11 states, which is 50% of the heat pumps in the US. So if we look at that population map again, this is where the ground source heat pumps are. This is the air source heat pumps. This is an actual map of residential heat pumps from a dealer. It's proprietary, but it actually showed installed installations in real time for 2025. And this map maps very well with this map as far as ground source heat pump installations. Not so much the density right here. That's probably more air source, but there's significant ground source installed in air source territory. And then you don't see anything in Florida, Texas, and California. California is not only prime for air source, but also it's an economic environment that's tough for dealerships, and we haven't invested in that. So moving forward to the next size, let's pick a target building type, which is optimal for what I'm going to propose in this presentation. So rather than being everything to everybody, like Henry Ford said, you can have any color you want as long as it's black. That's what we're talking about here. 88% of the buildings in the US, 4.3 million commercial buildings with heating and cooling, are basically between 5,000 and 30,000 square feet. 31% of those, or a third, use all electric heat. So they'd be perfect for ground source heat pumps, which is 3 times the efficiency for heating. And then what's really driving this is the actual building load. So a single family home is 5,000 square feet. I don't like rules of thumb, but if you use that for climate zone 6 energy efficiency type construction, it's about 7.5 tons. And you go light commercial in a climate zone 6 is 60 tons of capacity, which is kind of the upper limit of smaller ECM circulators like the Magna 3 or Taco heat pumps. And then the building that I've drawn here is 3 floors, 10,000 square foot floor plate. And then we have 30 bores at 500 feet. As far as a ground source heat pump design, you can put all 30 bores on one loop and bring in a flush cart from Iowa to flush that thing out every time it needs maintenance. It's not serviceable very well, and you might also have manifolds buried out in the field. But you could also do 5 sets of, you have 6 circuits with 5 boreholes per circuit, or you could have 5 circuits with 6 boreholes per circuit, or you could divide this up any way you want. But the optimized design, which I came up with, which is what we would do if you went to Forge Geo, is you might have this requirement. You say, look, I got 30 bores, 500. How can I optimize the efficiency so that it makes maintenance easy, flushing easy, it self-purges air in it when it's running, and it's also very low feet ahead through the design. So I balance the Reynolds number, which is turbulent flow, with the flow rate, which is excess pumping head that I don't need. So for this design, just as one example, the pump station's for 62 tons, 186 GPM, and that's really an ideal range of using dual variable speed pumps. The supply and return circuits are 3-inch SDR11 piping, which is pretty easy for any ground loop installer to put together with butt fusion. And then the ground heat exchanger is divided into 3 20-ton circuits. So there's 3 circuits of 10 bores at 500 feet, 1 1/4 inch. The flow rate 6.2 gallons a minute, which gives you turbulent flow. Yet the maintenance for this system can use a standard flush cart, 54 gallons a minute. So this would be an optimized design for that ground heat exchanger and allow you to implement it and not really look back. Like, it's going to work once you built it. So what we're going to talk about is 4 aspects to implementing heat pump systems. One is the pumping side, which is the example I told you, which is pumping through the ground heat exchanger. But then there's pumping through the building itself to all the heat pumps. Traditionally, we use one pump between the heat exchanger to the heat pumps. So the flow rate through the heat exchanger and the flow rate through the heat pumps is the same flow rate, and that's not really an optimal design. Another area to look at is hydronics. Doing distribution and layout of hydronic systems easier for zoning. It's more efficient, as I mentioned before. And all of these modules you can buy off the shelf, and then the module for this you can buy off the shelf. And I'm suggesting doing that instead of trying to build the engine by yourself. This is an example with water to air units and water to water units in the same building. We are not going to talk anything about forced air distribution. There's no optimization there for us to discuss in that. But you'll see with a building like this, the most optimal design would be the ground heat exchanger has optimized flow pumping. Then you distribute these residential size heat pumps up to 6 tons throughout this building, which gives you air zoning. And then if these are variable speed water to air units, they can automatically zone up to 6 individual zones within that one heat pump from the onboard controller. And that greatly simplifies the installation and operation. So what are we focused on? First of all, redesigning the heat exchanger and heat pump. We want to minimize design risk with automatic balancing, which is really difficult the way we currently do business. We're going to optimize the ground heat exchanger operation with built-in temperature control so that you don't have to worry about flow rates and figuring out a flow rate that gives you the best performance of the ground loop. It's done by the onboard pump controller. And this reduces pumping energy by 50%. And it's modular and repeatable so that you can use standardized pump stations for the building sizes that I talked about. If you configure the heat pumps for dual process applications, you reduce the size of the ground heat exchanger. So a heat pump that has a COP of 3.5, if it's simultaneously heating one source as it cools another, that's a COP of 7. That also reduces your ground heat exchanger cost because it's not load on the ground heat exchanger. It's a direct payback from one to the other. For a hospital in Vail, Colorado, a hotel in Vail, Colorado, they had a constant 12-ton cooling load even in the middle of January, and they had a hot water loop and a cold water loop. So by putting in a 12-ton heat pump that heated the hot water loop by cooling the chilled water loop and running 24/7, the payback was literally 18 months without a ground heat exchanger. It also allows you to configure campus or localized thermal energy networks into the pumping station, which I'm going to talk about a little bit later. And finally, with hydronic distribution over forced air, if you're fighting against VRF or mini split systems, you can use radiant cold and hot water tanks with distributed fan coils. And it's easier to simplify zoning. You can see the zone map. Those are floor zones and radiant flooring, but they could also be fan coils. Instead of running ductwork, you're running piping, which is more efficient. It's faster, installation is cheaper, And then the one thing we are going to talk about is a dressing kit, which is all the parts and pieces that hook onto the heat pump. And I have a picture of that on the next slide where, let me move my slides over. You can see that the dressing kit has everything that you need for, like in this case, a water darter heat pump. It includes the load pump. It's got flush ports as well as TP ports and everything else. So you can actually operate this ball valve with this one and you or that one, and you can actually flush out the heat exchanger independent of the ground loop. And you can order those as one complete kit that allows your installing contractor to very easily install all the parts and pieces and the heat pumps configured for perfect optimization. When you talk about this architecture being modular, at the 2017 IGSHPA conference, our company did a display at the Denver conference. And this is a 2 million BTU system, 1 million BTUs of high temperature heat pump capacity. And that's for 8,000 square feet of snowmelt. And because carbon taxes were relevant in Pitkin County, Colorado, that provided a $350,000 savings to the homeowner in offset rent fees because it was electric, but there was a backup boiler that was 1 million BTUs. So that was a very financially successful project for the homeowner because he ended up paying with the tax credit about $450,000 for $1 million system. The next thing that we'll talk in detail in the next several slides is using integrated pump stations. And basically it handles the ground loop pumping and the building pumping at the same time. These hydronic distribution panels are also another thing you can use if you're using fan coils or radiant floor. All of this equipment here is manufactured by GeoFlow. You guys would know Tom Wire and GeoFlow as a leading developer of integrated pump stations in the United States. So if we look at the typical way of doing business, when I got started in 1999, we used rules of thumb of 200 feet per ton, 3/4 inch downhole piping, 1 1/4 inch supply and returns, an FC2 flow center that looked like this, or it was white box with 2 pumps hooked up to the heat pump. And the flow through the heat pump and the flow through the heat exchanger was the exact same flow. And that was basically how we did business. And we put them in for all the residences. And then you get into bigger configurations, slightly bigger houses. And now let's say you have 3 heat pumps, you basically duplicate the same 3 things. And if all 3 heat pumps are running, you're assuming that the flow in the ground heat exchanger and the flow in the heat pumps is optimal. And you have balancing valves, which all balancing valves are, is restricting your flow so it increases pumping energy, which is really not a good idea. But this is easily understood based on the prior example. And then if you go forward to larger buildings, let's say a light commercial 24-ton building, now instead of having balancing valves, we have control valves that open and close when the heat pump turns on. And we have either a fixed speed pump, which hopefully we don't anymore. You use variable speed, or they use the VFD with a fixed speed pump. So you have an inefficient pump with a modulating electronic controller that slows down the speed of the pump. But it's really not more efficient. It just has the pump run slower. And that's the only efficiency. It's not in the engineering of the pump. It's simply using a controller to slow down or speed up the pump speed. And so we basically are circulating the flow through the heat pumps with the ground heat exchanger with a single pump. And if we wanted redundancy, they just add another pump. Where in fact, you'll see on a follow-on slide, if you want 85% redundancy, which is what you need for most buildings except for hospitals and data centers, you're in a situation where you're able to run 2 pumps at lower speed and make a very efficient configuration for your building. The other last thing I'll talk about this is that we always use reverse return on the ground heat exchangers, but many times I'll see drawings even today where engineers will design the building without reverse return on the heat pumps. And so if we go to the prior slide, this does not have reverse return. This heat pump gets all the flow, this gets minimal flow. And if we're trying to set this pump for this speed with this configuration, you're going to be over pumping your ground loop. Excuse me, you're going to be over pumping your building. So Tom Wire gave a presentation at the last IGSHPA conference By the way, I've been going to IGSHPA conferences for 20 some years, and this was the best conference I'd ever attended. I would highly recommend you consider signing up to go to the conference in St. Charles in 2026. I attended maybe 10 presentations. I downloaded slides from another 10. So I downloaded slides from about 20 different presentations, and I refer to those all the time as most state-of-the-art references for what people are doing in our industry for competitive advantage. But in this case, we use the idea of the single pump where we have a dedicated circulator, and then we put smaller pumps to match the head pressure of the individual ground source heat pumps into a circuit so that anytime the heat pump turns on, it turns on its local pump. Again, with DDC, this does not have to be a DDC function. If this pump only runs when that heat pump's running, wire it directly to the heat pump and don't worry about it. Just pretend it's part of the heat pump module, and you basically hook it up and forget it. This pump is going to be modulating on delta P, or a change in pressure. And so as more and more heat pumps come online, it's going to increase the speed to increase the pressure. And again, you've got the same flow rate through the ground heat exchanger as do the heat pumps. Need to back up for a second and just mention that we typically design for full load, but 87% of the time the heat pump's running at a partial load. The way that affects power and energy is that 80% pump speed is 80% flow rate. So it's 1 times the speed. But it's the speed of the pump squared, which is a feet ahead. So at 80% speed is 64% of head, which means you can use lower head pumps to get that performance. But it also uses half the power of running 100%. But if you look at heat exchanger capacity, there's some really good analysis that says we typically design for 3 gallons per minute through this heat exchanger, but on a thermodynamic analysis, if we have 80% of the design flow, so instead of 3 gallons per minute, if we only had 2.4 gallons a minute, we would still get 95% of the heat exchanger capacity. So that's something where you design it for the maximum load, but you might run it at 80% unless you have an issue, and then you increase that speed of the pump as required. And if you have 2 pumps that are designed for 70% load, it gives you 85% redundancy. And there's some information out there from major manufacturers that talk about that. So what happens if we hydraulically separate the ground heat exchanger from the heat pumps? So you put a tank or a heat exchanger in the middle. What you can now use is you can use change in temperature control or differential temperature on the ground heat exchanger. That does a couple things for you. First of all, it's not an arbitrary flow rate based on arbitrary thermal conductivity. What you're actually measuring is the differential temperature across the heat exchanger, which in real time is compensating for building load, thermal conductivity, and all those things that we design for. So it makes it safer for you to design by doing hydraulic separation, and that the pump's going to run at whatever speed it needs to maintain the change in temperature across the ground heat exchanger. So if you have very little load, that pump may be running very, very slowly because the heat exchanger design, let's say it's designed for 10 heat pumps and you're only running 1, that flow rate might only have a 2 or 3 degree delta T because there's no load. So that pump's going to run on the slowest speed. As more and more heat pumps come online, the delta T is going to increase from 2 to 3 to 4 to 5. And you might set it saying, okay, anytime it goes over 6 degrees, I need to speed up the pump speed to control the temperature differential against the heat exchanger. And that's real-time dynamic for the optimum speed for the heat exchanger. On the change in pressure side, it's using the same logic we used before, where we have control valves and we have differential pressure. But the one thing with this, according to NREL, is it causes some overpumping in certain circuit situations. So for high head pressures, we need a dynamic reset. And I'm going to show that in a subsequent slide. So this is what it looks like when you implement the ground heat exchanger with hydraulic separation. And then you have the pumps on change in differential pressure with dynamic reset. So the highest head pump, or the, in engineering terms, minimally open valve is basically the lowest flow rate through the system. If you use delta T across this heat pump, you're doing the same thing. If you maintain a 5 or 6 degree delta T, which is the manufacturer design requirement, it's going to modulate based on the temperature going through the heat pump, which is more accurate than just having an arbitrary compressor speed to modulating valve. But also you can use this as a dynamic reset for this pump. So it's pumping too high or too low, you can modify that. So the pump with the greatest challenge on the system is actually overriding whatever the constant pressure setting is. And that comes right out of Department of Energy guidelines and national labs. What this looks like is it looks like a 12, 8, 10, 12, 14, 16 inch tank separator. And then it has ports for each side. So my ground heat exchanger is going through the ground heat exchanger and coming back to the pump. So it goes this way on this side. So the flow rate is down the column. And then the building itself is pumping this way, which is up the column. So you get all your mixing in here. And this is typical specifications that we provide to GeoFlow with the design. And it basically says, I need this many gallons per minute at this feet ahead for heat exchanger 1. I need this many GPM at this many feet ahead for heat exchanger 2. And then we design the pumping and the pipe sizes. So this could be 2, 3, 4 inch flanges on this pump station, and it optimizes the heat exchanger flows. And it also, you can have different flow rates. So this could be 42 gallons a minute. This could be 80 gallons a minute. It really doesn't matter. It's sized for that application. What it helps for district energy systems, or for example, the Vail Library, the ice rink provides heat to the ground heat exchanger. So what we can actually do is have a third set of 2 ports, and that goes to the ground heat exchanger for the building next door. That has its own flow rates with its own head requirements. So it provides seamless integration with the ground heat exchanger. Or a solar thermal array. If you have a solar thermal array that's going to augment your ground heat exchanger and provide additional heat, you can just hook that on as one of the ports. And these don't have to be balanced. You can have 6 ports on this side and 4 ports on this side, and it really doesn't matter, just mixing the water. So it gives you infinite flexibility, but it ensures the design's going to work. And then mechanical room A, in this case, it might be 4 heat pumps or a couple heat pumps. And then in this one here, it might be 6 or vice versa. In this case, we have a big flow requirement for all the heat pumps in the building because several of them are cooling only and some are heating only. So they offset the ground loop demand, but I still need to get the flow rate through the heat pump. So in this case, I have a higher flow rate on the building side than I do on the heat exchanger side. If I use the old method of designs, I'm going to give the ground heat exchanger 180 grams GPM, which is dramatically going to change the supply and return piping. Like in this case, it's a 2-inch supply and return 340 feet versus 3-inch pipes 540 feet. I might end up with 4-inch pipes on this side, which dramatically increases my cost, flushing requirements, and complexity. So if you use factory built custom components, you can have up to 4 heat exchanger circuits, which is basically 8 ports and 4 building circuits, up to 60 tons of capacity. And as I mentioned, it integrates ground source heat exchangers in the process. So I want to talk about intellectual property just quickly. As I said, Energy Environmental Corporation has patents on this. If you're buying the pump station from GeoFlow, basically you're covered. You don't have to worry about any kind of patent infringement or anything. If you're designing on your own, you should probably call me to make sure you don't infringe. But you can actually review the patents. There's 8 of them in a pending application, which is at the patent office. But if you search Google patents under 121888676, that'll give you the latest patent. And you can read the specification. The specification is the same for all the patents. It's the claims that are different. This is one that specifically talks about what I'm talking about, this presentation. And we're using delta T control on the heat exchanger side and dynamic dew point control on the building side. I have many engineers saying, well, anybody can design that. Well, that's true. Anybody could. But if you were going to do that back in 2012, you should have applied for a patent. ASHRAE doesn't mention it until 2015. They talk about differential pressure control, but they don't address delta T. Oak Ridge National Laboratories in 2017, for the first time, came out with variables pressure control with delta T on the ground heat exchanger side. NYSERDA has since adopted that, saying If you're using central pumping, use it for delta P and then delta T on the loop. And then there's an excellent presentation you can download from the IGSHPA website by Tom Wire at GeoFlow. He has a presentation tackling large jobs and retrofits. It's the IGSHPA 2025 conference. And he discusses the hydraulic separation I talked about using a case study that our company did in Texas. So the 12 steps which are addressed in the plumbing engineering article, which is also another course in itself. The most critical thing that you can do as an engineer or designer is understand what the client's objectives are. They're not going to be thermal conductivity. They're not going to be pumping speed. They're going to be energy efficiency, sustainability, ease of maintenance, ease of operation, simplified controls, those things that I talked about. The most successful project I've seen for large net zero energy buildings use a design charrette. So the architect, the engineer, the designers, installers, energy manager, they're all in the same room and they're talking about what are the resources on site, what are the things that we can integrate, and what are the goals of the owners. You do a comprehensive site review to check out geology, overhead power lines, and there's many things that article talks about. Mandatory is detailed hourly building analysis to understand peak loads, but also building loads, and then heating degree day and cooling degree day imbalance that I showed you with the ASHRAE numbers. Assessing the ground thermal properties. We tend to run a TC test and say, okay, now is it profitable? That would be a mistake. From local drilling logs or geotechnical data on the building, you can estimate the thermal conductivity, and it's not going to change. For most projects, it's not going to change the financial analysis by more than 10%. So I first would do the analysis using existing technical data, and then I would verify with thermal conductivity when you get into detailed design with a TC test. But if you do the TC test first, you're doing it backwards. It's actually being lazy and not doing your homework on estimating soil conductivity and diffusivity and moisture content in the soils from available data. And then you want to look at site-specific thermal properties. In this case, waste heat use from a data center, seasonal thermal energy storage. That could be a tank. You could also use a ground heat exchanger for solar energy storage, because the greatest challenge with solar thermal systems is in the summertime, the tanks get really, really hot, so you need excessive tanks to store the extra energy. But in the wintertime, you don't have enough solar panels on the roof. So it's always a balance of how to get more storage. You can use solar thermal applications for that. A very interesting application was a dairy farm application I did for a grant with the Department of Agriculture in Colorado. And we cooled the milk by heating the washdown water. So by balancing the loads between cooling the milk from 98 degrees in the cow or whatever it was down to 34 degrees, we were able to heat the washdown water. So every 8 hours, they use high temperature washdown water and just boosted it with a boiler. And that's a source process heat exchanger integration. You also want to plan space for your mechanical equipment. It's very rare that I find a set of plans that has adequate space, but when I go back to the architect and the owner, they're able to make it when I say it's a mandatory requirement. For any residence, it's 200 square feet. If we're doing a larger building, it's 3% of the building load. And then that actually allows you to design a space that compensates all your equipment. And you want the greater of 200 square feet or 3% of the building envelope for your space. You want to hydraulically separate the ground and source loops because the optimized flow is not the same. As I said, CSA 448 says that the ground loop flow needs to be balanced and then the source loop needs to be balanced. So both sides are supposed to be balanced, but if they're always the same flow rate, that's really difficult to balance. It also assumes that they're this exact same flow rate for the best energy efficiency, and that's rarely the case. Look at a pumping strategy. We can help you with that through Forge Geo as a no-cost service. And then I talked about a case study using iterative design. What this is, you could put all 30 loops on one circuit with one big pump, where you could divide it into 3 circuits with 3 pumps, or 5 circuits with 5 pumps, or however you want to do that, or have multiple circuits combined to go through one pump. But the size of the piping, the size of the ground loop, the flushing requirements are all balanced to balance the cost, performance, and the long-term temperature stability. When you run delta T, NREL has said that it automatically provides balancing for your ground heat exchanger and enhances thermal stability. Heat transfer fluids is also another concern. With propylene glycol, if you look at Dow Frost and some others, you need 25% concentration minimum for corrosion inhibitors. So if you need a 20% for antifreeze and you don't add anti-corrosion inhibitor, that is going to cause degradation of your equipment. If you use something like Fernox F1, what I do is I'll design the glycol for my antifreeze requirements for freeze protection, but then I'll just add the corrosion inhibitor as opposed to automatically mandating 25 or 30% just because I want the corrosion inhibitors. You also should provide very good construction documents. Again, I'll recommend you go back to the IGSHPA conference 2025. Terry Proffer, a good friend of mine here in Colorado, he did an excellent presentation on documentation for ground heat exchangers. I talk about it in that plumbing engineering article, but you should put all the information for the ground heat exchanger and the heat pumps on one page. Some engineers will put across 10 different pages the schedule, the heat pump flow rates, the ground heat exchanger layout. But the contractors that are building it, especially the ground heat exchanger, everything they need to know should be on that same page. And then don't walk away from your design. Show up whenever they're drilling, headering. Check grout density. Just measure a pound of grout. It's pretty easy to do at the top of the hole and make sure they're using the right mixture. So we're going to switch gears very quickly from the technical side and get into Forge Geo. Forge Geo is an organization of, Forge Geo Incorporated is a nonprofit Colorado corporation, but Forge Geo is an organization as a team working together to expand infrastructure, first in Colorado, then nationally. But the intent is to train current and future geothermal workforce, deploying modular solutions to enhance energy efficiency. Training is a lot easier if you're training to an approved solution. So instead of teaching somebody how to build an engine, how to build a transmission, how to put all the parts and pieces, you're saying, buy the transmission, buy the engine, bolt them all together, and here's how it goes together like Legos. And that greatly simplifies training and enhances the reliability and the actual performance of the system that was built. When GeoFlow puts these pump stations together, all the flush ports are in the right place. The pumps are configured to give you the proper flow rate, counterflow, and everything else. But Forge Geo as an organization uses public and private funding to expand the workforce to lower the costs and accelerate adoption in the U.S. You can see here the team. There's Colorado Energy Office with Governor Polis, the Geo Exchange Organization, Mission Geo, IGSHPA is part of this, GeoFlow, Water Furnace. There's a couple other manufacturers interested that are playing with this. Colorado Water Well Contractors, ISCO Pipe. And then for getting people into our pipeline to get certified and trained is Goodwill of Colorado. Goodwill nationally works with workforce centers to get people that are not in the trades, the training and certifications to get family supporting jobs. We also have Disabled American Vets. They got a database of 30,000 people looking for jobs, getting out of the military. And there's some exciting opportunities with the Army and other programs where they will pay to get soldiers trained to have civilian jobs. Interplay Learning is an online platform for maintaining core certifications. So before you learn about heat pumps, you need to know about refrigerants. You need to know about HVAC systems, electrical systems, and you may have to also learn about basic things like math, design, reading a slide rule, etc., and it covers that. So then the last point I'll mention on Forge Geo is that we have a design assistance program right now. If you go to the forgegeo.com landing page at the bottom, you'll see different checkboxes you can sign up for. And you would want to check the obtain designer engineering services, and you can register to be part of this First 10 program. The First 10 program is energy efficient building envelopes, 5 to 30,000 square feet for new and retrofit construction. You have to provide hourly heating and load calculations, preliminary technical data, and then you have to source the pump stations from us. If you don't, you're liable for patent infringement, or you have to have a license fee. We can talk to you about that, but this makes it all go away. Just like you buy a pump station or you buy an iPhone, it includes all the intellectual property included in that. But what we provide you, which you don't get from just building a pump station, is you get 1 day of on-site consulting, and post-installation support. You just pay travel and lodging. We also provide you with designer or skill certification with Forge Geo. And if you want to integrate hydronic systems, we have the ability to design those radiant panels based on the size of the system and the building that you have. If, for example, you had a 30,000 square foot building, this panel handles 10,000 square feet. You'd put one panel per every floor and you'd be good to go. So that was kind of eating 25 pounds of potatoes in a 5-minute time slot. This is the end of my presentation. Here's my contact information, my phone. If you want a copy of the slides, send an email to info@IGSHPA.org. If you want to see this webinar again, you have the link since you're clearly watching it. And then you can also send an email at alwallace@energyhomes.org. If you have any questions about this presentation about energy, environmental, or Forge Geo. So back to you, Greg, and you pick up any questions you have from the audience.
Okay, very good. Thank you so much, Al. A lot of content, a lot of good information there. My goodness. Yeah, they probably want to review this when they're done, I think, because there's so many things you provided. So that's a really good presentation, and we appreciate your doing this today and sharing the information with everybody. So let me take a look at the questions maybe that popped in here through either chat or the Q&A. See if we got some. Yeah, I think we got a couple of them in here. So let me pick one out. Give me just a second. I'll queue it up. Yeah, let's look at this one. So here's a question someone's asked. What are the key limitations of older ground source heat pump heat exchanger design methods, and how does this new approach address them? So maybe you can answer that, Al, the
Yeah, I think
changes between the old method and the new one that you're presenting today.
Yeah, according to Department of Energy and also the national labs, you truly want to separate ground heat exchanger flows from building flows. Those are not optimized, and it's very complicated with higher head, higher pumping energy to try to pump both at the same time. It's
Okay.
better to have a hydraulic separation. So that's the first thing, is your piping layout is going to hydraulically separate those two, where in the past, they were integrated so the same flow went through the heat exchanger and the heat pumps. The other aspect of that is when it comes to control, you're going to control the ground loop on change in temperature, which is very precise. And it compensates for a lot of design oversights or problems where the pump will automatically speed up flow or slow down flow to optimize that. And that's by simply adding another temperature controller to the pump, and it does everything on board the pump. You don't have to program anything to do that. And then the way it varies with the new system too is that those heat exchanger designs are optimized that when you buy a modular component, you buy it from GeoFlow and it's built by the factory with design quality assurance, not only in the construction, but also the ports, the flushing and everything else is fully integrated with temperature gauges and things that you would need to run that pump station. So you don't have to worry about specifying it or hoping that your engineer builds what you designed.
Okay. All right. Thank you for that. All right. I got another question here. Someone's presented to us. Could you elaborate on how iterative modeling enhances system performance and reliability?
Yeah, so this is the example that I used with the 30-ton ground loop, or excuse me, the 30-bore ground loop. When you first start off, you do the calculations and it says you need 15,000 feet of ground loop capacity based on thermal conductivity. Well, that could be 30 boreholes on one pipe. So now you have to iterate and say, okay, what is an optimal design for flushing, for example? Well, I can't exceed a certain flow rate and I can't exceed a certain set of heads. So I'm going to divide that into 3 separate ground loops, each with 10 circuits apiece. And then you run some more modeling and say, okay, should that be 1 inch down the hole or 1/4 inch down the hole or 2 inches down the hole? And you say, okay, to get the Reynolds number up, I don't want 2 inch, I'm going to use 1 1/4. But if I go to 1 inch, I've got a Reynolds number of 10,000 and my pumping energy is off the charts. So you iterate and go through that modeling around and around till you get the optimal design for flow rate, for flushing capacity, and then layout. You don't want to have a remote manifolds buried in the middle of the field if you can get away from that. You want to bring everything into the mechanical room, but you got to balance the size of your supply and return piping and ensure that all of those work together. And that's kind of the basis of how iterative modeling helps to optimize design.
Mhm. Okay. Yeah. All right. Very good. Let's look at another one. Here's another one. So, the question submitted, what are the risks of relying on HVAC rules of thumb for system sizing of ground source heat pumps?
That's a great question. Dr. Listerbrook, who is a building science expert, said if you live in Atlanta, never let a Yankee design your house. The rules of thumb for HVAC in Atlanta is a lot different than New York State, but also things that I talked about, like we used to use 200 feet per ton using 3/4 inch pipe down the hole. That is, I haven't put in a 3/4 inch downhole piping configuration in 15 years because it's really not optimal. One, it's required by codes. CSA 448 clearly mandates that you have building loads. Even to apply for a building permit these days, you're supposed to have manual J, manual N, or trace train type calculations done. And so you'll run into problems. And if you are a designer, or even an installer, you can have liability because you didn't follow industry best practices in doing it. So it's basically a best practice that also sizes the system perfectly for the loads, assuming they're as close as you can get without oversizing or undersizing the system.
Hmm. Yeah, absolutely, for sure. Very good. All right, we're getting kind of close on time, so I guess we'll take this last question. We'll run this up to you, and then I think we'll conclude our webinar today. So, last question was, this is probably a great one for you, is what kind of training does Forge Geo offer for HVAC contractors and system designers? So maybe you can go a little farther on that.
So Force Geo has two responsibilities. One is to get people into the industry. So somebody's working at Starbucks, or there's a case where there's a nurse assistant wants to get into the technical aspects of HVAC. She's got a strong background in technical things, but she's not an HVAC person. So Force Geo covers what I call core courses: how to read a slide rule, how to do basic math, all the way up to how refrigerant circuits work for HVAC, how to diagnose electrical, and those are all online courses through Interplay Learning. And then after you pass those courses and you get the core down, then we offer those courses that you would typically get from IGSHPA, AEE, or whatever. And IGSHPA is moving toward a standardized course, which is not the accredited installer, but it's really focused on installation, service, ground heat exchanger installation, residential, commercial design. And so you have specific courses and certifications that are aligned with job roles. And Forge Geo is going to be right in the center of that. So we can increase the number of people coming into the field, but also we reach out to HVAC or existing geothermal contractors and upskill them to be more proficient in the jobs that they're already doing.
Okay. All right, very good. Thank you so much for all this information today, and thank you to all of our audience members who participated, watching the presentation and asking questions. So I think we'll wrap it up. We got kind of a good recording, I think, today for sure for everybody to watch. There was so much content. So if you didn't get it all, you can watch it probably in a few days. We'll have this on our website, and you can pick it up maybe again, maybe grab the concept you missed a little bit more you wanted detail on. And if not, you can send Al. He gave us his email address as well. You can go right to him and send him an email and ask him the question. And we'll try to follow up on anything that's submitted to us that we didn't get to today. So thank you very much, Al, for your time and the information. And thanks for all of our viewers for watching. And we will conclude our webinar today for the October Dig Deeper. Thanks so much, and have a great day.